In this use case, we're going to be looking at the window mode of the AVR ADC. So here we have set up the window to look for samples above 2.5 volts or below 1 volt. My starting point is an empty MCC Melody project for the AVR 128DB48. Though the API reference use cases paired with a board schematic should work for any supported AVR in MCC Melody. The video will give you an overview, but just remember to always check the API reference for the most up-to-date version of the use cases. So I'm going to start by adding 3 components to my project: an ADC, an RTC, and a data streamer. Streamer, ADC. Under timers, I'll find an RTC. So we get a warning here about interrupts because on the RTC, interrupts are enabled by default. So I can go to System, Interrupt Manager, and enable Global Interrupts. That warning now goes away. The other warning I can take care of is the dependency for the data streamer, and we know that that's UART3, PB0 and 1. So selecting UART3, we see that notification has gone away and that PB0 and 1 are the default. So we've taken care of our warnings. In terms of the ADC, we don't want the ADC left adjusted since we're going to use the full 12-bit result. Since we are using a window, we are going to enable the comparator interrupt. The window type is outside of window since it's the easiest to see on the PLIB data visualizer. Now note here, we wanted above 2.5 volts. So going back to the builder, we see that the voltage reference is associated with the VREF, which is a generic voltage reference for all analog peripherals. So we're going to give the ADC a voltage and use VDD as our reference. So coming back here, now you can see 5 volts, although checking our hardware users guide, supply, here we can see the power supply, and by default our C nano is at 3.3 volts. Okay, so we wanted 2.5 and below 1. So for the RTC, we want a period of 0.05, which is 50 milliseconds. Interrupt enable, yes. So now adding the ADC result and window count to our data streamer table. Yes, we've enabled the global interrupts, our pin for the analog input. So we are using the QRCD Nano base for clickboards. We have a potentiometer connected in microbus slot 1, which is PD4. So we assign PD4 as our analog input pin. We selected our UART, LED as output, renamed to LED, LED PB3, PB3, and other pins to LED. What we skipped over here is we need to also disable the digital input buffer on our analog pin. That looks like the configuration setup. So we're going to generate the code and add the following to our application. So we'll start by just putting this on our clipboard. Generate. So in terms of the code, we have a flag. Here you see the 2 callbacks. So our RTC callback, all it does is starts an ADC conversion on a particular analog channel. Remember that if you're using a different analog input channel, you will change it here. Then in the window, we toggle a LED. We get our conversion result. We come into this window callback when the ADC has evaluated its own sample and determined that it's outside the window. So the ADC conversion result is already waiting for us. Here's our main. No issues with compilation. Let's program. Okay, give ourselves a bit more space for the data visualizer. So in the data visualizer, importing giving ourselves more space, adding a debug GPIO. We set this debug GPIO low when we are in the window callback and high after our frame is sent. Okay, so now we'll start adjusting our potentiometer and looking to see how the window shows up. So the green plot is a sample number, and you can see that there are horizontal lines when we are in the window. Similarly, our debug GPIO does not toggle since we do not go to the window callback. So when using window mode, it can be useful to plot points. Since then no lines are drawn between samples and one can clearly see the window. And we can see here that the application is working as expected.